and present our today's speaker. The goal of this project is to create, consolidate, and join efforts from the local space network, expanding women's opportunities for leadership and professional development, while at the same time increasing their visibility in the aerospace community by creating a professional network. Today, our host speaker is Pilar Gil. She is a PhD in applied physics and nowadays is working as a professor and researcher at the Universitat Politècnica de Catalunya. Moreover, she leads a research group specialized in the astrophysics, stellar evolution, and nucleosynthesis. In this talk, she is going to explain us about the origin of the elements and all the chemical reactions that take place inside the stars. If you have any questions, you can write them in the chat during the presentation, and we will manage them after Pilar's speech. Thank you and enjoy this talk. Pilar, the floor is yours.
Thank you very much, and thanks for inviting me to give this talk. I hope you find it interesting. I'm going to talk about the origin of the elements. And now I want you to look around, look at everything around you, or if you don't want to, look at this fantastic picture by Van Gogh and think of the stars, of the trees, of the mountains, of the houses, of everything around us. That's made of atoms. Atoms can be of different elements. Where do those atoms come from? What are we made of? So this is the question I'm going to address today. In order to answer to that question, I will talk about how star lives and how stars live, and how do they make the universe evolve. So let's start. But before, a bit of nomenclature, because astrophysicists are funny people in some ways. And to us, the periodic table can be very simple. Hydrogen and helium are the non-metals. So perhaps I could move this. Sorry. Hydrogen and helium are the non-metals in the periodic table. The rest are metals. So to an astrophysicist, carbon is a metal, nitrogen is a metal, and oxygen is a metal. That's funny. Okay, if I talk about burning, I'm not going to talk about standard burning, when you burn wood or paper or coal. I'm going to talk about nuclear fusion. So burning is a big thing to us. And now, let me present a bit the outline of what I'm going to talk about. First of all, it's about the matter around us, then about the Big Bang, stellar evolution, and nucleosynthesis, actually. A bit about the oldest stars, because I'm rather obsessed with them in the last few years. And then very briefly about the history of the universe. Okay, in order to give this talk some perspective, let's discuss a bit the composition of the universe. There's a lot we don't know about in the universe. If you attended the lecture by Licia Verde, you probably remember that most of the universe is dark energy. About 72% of the universe is dark energy, and we don't know what that is. About 23% is dark matter. We know that dark matter behaves nicely with gravity, but still we don't know exactly what it is either. Before we go on, let me remind you, or let me tell you, that the first person who discovered the existence of dark matter was a woman, actually, Vera Rubin. When studying the motion of galaxies, she realized that there had been a lot of matter that we could not see and which could explain the motion of those galaxies. We will not talk about that fascinating subject today. We will talk about ordinary matter, which represents only about 4% of the matter universe or in the universe. And even though it's a tiny percentage of all that exists in the universe, it's very important to us, of course. Okay, don't be scared about this plot. It simply represents the relative abundance of the different elements in the periodic table in the sun. So this, what we have here in the vertical axis is logarithmic. So 1 unit represents a factor of 10 actually. And what do we have in the x-axis, the atomic number. So for 1, we have hydrogen. For 2, we have helium. 3 is lithium, and so on. What you can see is that in general, there's a trend, a decreasing trend. So as we advance to bigger atoms, so atoms with more protons, their abundance decreases. There are funny variations. For instance, if you look at the lithium, beryllium, and boron here, you know, this minimum, that can be explained easily because these are elements which are very fragile and they are destroyed in stars. And one important thing, the most abundant element is hydrogen. And the second is helium. And that's actually, as we will see, that's a proof of the Big Bang. One more important woman in astronomy, Cecilia Pinga-Pushkin, was actually the first person who realized that hydrogen was the most abundant element in stars, and actually it is the most abundant in the universe. She was discouraged about publishing her work because before her, there was quite established idea that the composition of the sun had to be rather similar to that of the earth, and people were even thinking that there had to be some fuel like coal or something like that which made the sun burn. Of course, things wouldn't work because if the fuel they were thinking about was what powered the sun, it couldn't have lived for so long. But still, she found a lot of problems to get her work and her important, her critical discovery acknowledged. So we know now, and we know thanks to Cecilia Pinga-Pushkin, that hydrogen is the most abundant element in the universe. And you will see later on why the rest keep decreasing. I thought I'd show you these funny ways of looking at the periodic table. Imagine that each box of each element in the periodic table were plotted as a function in terms of its abundance in mass. Sorry, in number here. So that elements for which there are lots of atoms have a big box. Elements for which there are very few atoms in the universe have a very small box. So the plot on the left shows what the universe would be like. So basically hydrogen, helium, and about 1-2% of metals. And remember, metal is anything which is not hydrogen or helium. If we think of us as human beings, more or less, our most abundant elements would be the ones which are shown here. So that's a funny way of looking at things. Let's go now to the very beginning, the Big Bang, very quickly, because I'm here to talk about stars. Well, at the beginning, we believe, and there are proofs which support this, that all the matter in the universe was condensed in a point with extremely high density and extremely high density temperature. At some moment, the universe started expanding in a tremendous rate, tremendous speed. At the beginning, during the first few seconds, only protons and neutrons existed. More or less, 3 minutes later, protons could join to neutrons and form some deuterium. Then some helium-3 could form, adding in another proton. And then finally, some helium-4. So just as the universe cooled down enough to allow these nucleons fuse together. Very shortly afterwards, the temperature in the universe was actually too cold to allow any further fusion. So just after the Big Bang, the universe was more or less 3/4 of, or 75% of hydrogen and 25% of helium. Only traces, a bit of lithium, a bit of boron, beryllium, and a bit of other stuff formed, but very, very little. Where did the rest of the elements come from? And here is when stars appear. I wanted to show you, this is one of the the foundational papers on star evolution and nucleosynthesis, actually. These guys, and between them there was a woman, actually. Here you have Margaret Burbridge, published this paper, which explained how the elements could form in stars. And I'm going to summarize this very briefly for you. Actually, a lot of what we are still doing is based on it's like adding comments on that fantastic piece of work. Okay, so let's start talking of stars. If you think of stars, what's important is the mass, the composition, and multiplicity. So they're a bit like pizzas, I like to say. So you care about whether the pizza is big enough, whether it's one or two, and what the pizza is made of. In stars, what's more important than the composition, so more important than what the pizza is made of, is the mass and the multiplicity, whether we have one or two or even more pizzas. Okay, let us think of how a star would be born. If you have a cloud of gas of the universe and that cloud is cold enough, it can collapse because, of course, gravity is always around. The cloud may collapse, the central parts of the cloud may collapse, become more dense, and increase its temperature. When the temperature in that cloud reaches about 10 millions of kelvins, 10 million degrees, then nuclear fusion or nuclear burning starts, and the star is born. Most of the time of the life of star, it's a big ball of gas which is in hydrostatic equilibrium. Equilibrium, this means that the tendency to collapse due to gravity is compensated by pressure. And what causes that pressure, which may compensate gravity? Sorry, that is nuclear reactions. It is actually the fusion which compensates, which allows to provide the pressure which compensates the gravity. If you think of more massive stars, of course, gravity is stronger and they need higher pressure to survive, to keep this hydrostatic equilibrium and higher temperature. Then, if we have higher temperature, then it's easier to have more nuclear reactions. So these big stars burn their fuel very quickly, and actually they have shorter lives than tiny stars. I will go back, well, I will actually use this fact later on. Okay, so what would a star, a normal star, like the sun, which is very important to us, but it's a rather common star, would do along its life? Well, we have a picture of how it would be born, and then then what happens later is that this fusion of hydrogen, which started, of this hydrogen burning, which started at the core, at the nucleus of the star, is extended in an inner region, which actually we call the core. And as a consequence of nuclear fusion, we do not only keep the hydrostatic equilibrium, but also we transform matter. We transform hydrogen in helium. And that all happens in the core of the star. Actually, our sun is doing that right now. Life is possible on Earth thanks to those nuclear reactions which are happening in the core of the sun. If we have a star more or less like the sun, in about 10,000 million years, the fuel, the hydrogen, will be exhausted in the core. So we will run out of hydrogen in the core of the sun. There will be only helium. And then hydrogen burning will start occurring in a shell around the sun, in a spherical shell, around the core of the sun. In that region, the temperature is still high enough for nuclear reactions, and there is hydrogen, so it will be burning there. And that moment, the sun will do something very spectacular, because it will grow to the size of the giant. and it will increase its radius in hundreds of times. And of course, it will become much more extended, and life on Earth will not be possible, I'm afraid, at the moment. Actually, even before that. Okay, once, what happens then? Do you remember this core in blue, in dark blue at the center, which was formed of helium? Well, because in that core there are no nuclear reactions, it will start collapsing, therefore increasing its density and its temperature. Well, when the temperature of the core of the center of the star is about 100 kelvins, then helium will start burning again and will develop around the core. And we will convert helium into carbon and oxygen, all that inside the core of the star. Just as it happened with hydrogen, after helium is exhausted in the core, it will start burning in a shell. And actually, the last active phases of the star, or nuclearly burning interesting phases of the star, will be fun because it will be hydrogen and helium burning in shells, alternating burning. So now hydrogen is on and helium is off, and then hydrogen will be off and helium on, and so on alternatively. We call that the thermal pulse in a GB star. Doesn't matter. This part is just the last before the complete ejection, or when it occurs, the complete ejection of the envelope of what is not the core in the sun, in the star, will be ejected to the interstellar medium, and will leave beautiful images like planetary nebula, which we will see later on. Okay, what happens? Well, actually, as I said, the sun stops here. But what if we have a much bigger star? Imagine a star which is 10 times bigger than the sun, or even bigger. What's going to happen? So it will not stop with helium burning. Carbon will burn as well, and oxygen in the core, and then neon, and then magnesium, and then silicon. And it will be burning in the core, getting a sort of onion-like structure, and a core made of iron. So once we get this composition, this iron core, because iron is so stable, it has the highest bounding energy, as we say, you cannot get more energy by fusion. And if we cannot get more nuclear energy, we cannot get the pressure we need to sustain the star. And if the pressure cannot win or cannot be there, then what's going to happen is that gravity will win. So the entire star will collapse, and that it will bounce back and experience a huge explosion, which we will call supernova. So, okay, I have been telling you about many funny things going on in the star. Once some atoms being converted into other atoms, but how do those atoms go out to the interstellar medium? Well, we have talked about explosions just now when we talked about supernovae. We talked about winds. So this phase of the star, when the hydrogen and burning shell were burning, in that time, the stars experience strong winds, especially at the last stages. And also, there are during many parts of the life of star, there are mixing between different layers. So between layers in which nuclear burning does not occur, like the envelope of the stars, and layers in which there is nuclear fusion. So these layers can be mixed, and so some material which was in these supernuclear bombs could be ejected to the, or could be transported to the envelope and finally ejected to the interstellar medium. So just a quick summary. I'm not sure you can see this. Sorry, perhaps just for a second, then I will go back to the big presentation. But I want you to have this picture. So I'm dividing the world of stars into non-massive and massive. into single and binary. So remember the pizzas. We care about whether they are big or not, whether we have one or two or many. Okay, if we have a single non-massive star like the sun, what we will get is a planet's nebula at the end of the evolution. I will talk about more later. If we have a massive star, which is single, then we will have a core collapse supernova. So just what I described, remember this ion core and the star collapsing and then bouncing back and this huge explosion, that would be a supernova. Okay, if we have non-massive binary stars, we could have as an outcome at the end of the evolution another type of supernova, which we call thermonuclear supernova. And if we have two massive stars together interacting, we could have a binary neutron star. Okay, what happens after at the end? What do we have left at the end? Well, for a star like the sun, non-massive and single, we would have a white dwarf. A massive single star would leave us with either neutron star, if it is not too big, maybe up to 20 or 25 solar masses, or a black hole, if the star is bigger than those 20 or 25 solar masses. If we have a thermonuclear supernovae, well, we will be left with a remnant, which eventually disappears. So there will be probably nothing left, or perhaps a bit of a core of a core which will look like a very tiny white dwarf, but we are not sure about what happens actually. Probably in a standard thermonuclear supernova, everything would be ejected. And finally, if we have two big stars, two big neutron stars, eventually they could coalesce, they could merge, they could become one. And as an outcome, we would either get a big neutron star or even a black hole. And then, of course, the creation of gravitational waves, or the emission of gravitational waves. Okay, we can go back now to the, okay. So again, another big woman in astrophysics. This is Jocelyn Bell, who discovered the first radio pulsar. Radio pulsars are the observational counterparts of neutron stars. And these objects helped us to confirm very important theories in physics and in astronomy. So the finding actually deserved the Nobel Prize, not for her, but for her collaborators, actually for her PhD advisor. Okay, so in terms of the material which each type of star forms, think of the carbon, which is critical to all living organisms. That carbon is formed mostly in single massive and non-massive stars. Nitrogen, which is in the plenty in the atmosphere, or you want it in the soil if you want to grow healthy vegetables, that comes from non-massive stars. Sodium, magnesium, silicon, all these, oxygen was formed massively in massive stars. Other heavy elements like barium, strontium, and mercury in non-massive. If you like really expensive things like gold and platinum, you have to go for massive. So these merging neutron stars. and for non-massive, binary stars would form lots of ions especially, and that's very important. Well, these results were presented in a fantastic way by Jennifer Johnson, a fantastic astronomer in US, and she presented each box of each element in the periodic table and showing mostly from which astrophysical site it came from. So as we know, hydrogen and helium formed in the Big Bang. Lithium can also form in dying low mass stars. So these single non-massive are these yellow ones. So the merger of neutron stars produce very heavy elements. So the last ones in the periodic table, or supernovae, produce the oxygen, the fluorine, neon, sodium, magnesium, all these. And for the iron, for the nickel, you have to go for these exploding white dwarfs or thermonuclear supernovae, as I call them. Okay, let me talk for very briefly about a subject which actually has been obsessing me in the last few years, and this is the oldest stars in the universe. Okay, when did the first stars in the universe form? Well, when the universe was practically a baby of 400 million years. They form, well, of course, if there's no stars, there's no galaxies. So we couldn't say they form in galaxies. They form in halos of dark matter, which were probably about 1 million times the mass of the sun. Actually, we know that if we think of stars formed more or less at the same time as the sun, so we think of new stars, we know that much more frequently small stars form. And as the mass of the star increases, less of them form. So at the end, what happens is that we have many stars like the sun, or even less massive than the sun, and very few stars which will be able to become a supernova. Well, we don't know if that occurred in the primitive universe. Actually, up until the last few years, people thought that only massive stars could form. But in any case, from what we have seen, because massive stars live faster, they were probably the first to pollute, to enrich the interstellar medium in metals. How did they evolve? Which matter did they eject to the interstellar medium? Can we see the oldest stars? How can we tell that star is old actually? Because they have no gray hairs or things like that, or they have no wrinkles. So how can we say that? Actually, how can we answer those questions? And what we do is models. So we have models of stars which explain all the physics and all the chemistry of the stars in our computers. And we say, okay, if we have this type of star, it should produce these elements. So are these elements what we see in all the stars which we observe? Well, this is of course work in progress and very interesting one. Okay, a couple of aspects. How can we say that the star is very old? So as I said, no wrinkles, no gray hair. So of course, the oldest thing which we know in the universe is the Big Bang. So the more a star looks like the matter of the Big Bang, the oldest it should be. So very old star should be mostly helium and hydrogen, very little metals. So much less metals than the sun. And what would a first star look like if we saw it today? Because we know that if a first star formed with 0.8 times the mass of the sun, it could still survive. It should still be there, but it would be very faint. It would shine very little. And it should have pure hydrogen and helium. Again, very little metals. But on the other hand, it could have been polluted by matter from other stars. So even if we saw one first star or the daughter of the first stars, it would be difficult to recognize. Okay, there are many large, interesting observational surveys looking for that, but the most metal poor stars are very elusive. So what are the records? If you think of the most metal poor stars observed, metal poor means very old, observed, what are we looking for? So it would be a star which has millions of times less metals than the sun. And these guys have been observed. And that's spectacular. That's really taking us very close to the beginning of the universe. So, well, close, but 400 million years or the first millions of years or the first 1,000 million years. And why are we so excited about them? Well, stars which we know today, which have the age of the sun, show the matter synthesized by many other stars. But those very primitive stars show the matters synthesized probably by one or a few stars. So they are our laboratories, and we love them. Okay, so as I told you, how can we know things? We have to be good detectives. We have to be good superhero detectives and compare what our huge stellar models do to what stars look like, what these metal spore stars look like. And apparently, all the supernovas make quite a good job. But also, eventually, non-massive stars started contributing at some moment. When did they do that? So this is the sort of things which we want to know. And just to finish very quickly, the history of the universe. It doesn't seem quick, but it's going to be. So remember the Big Bang, about 380,000 years, the first atoms could finally form. 400 million years, the first stars. About a billion years, the first, or 1,000 million years, the first galaxies. And they kept evolving. Okay, let me show you here how stars actually recycle matter, or how galaxies recycle matter in the universe. So we know how star is born. It forms in a molecular cloud, so in a gas cloud, which is cold enough to collapse and then reach high enough temperature in the center. So this 10 million degrees, start nuclear fusion of hydrogen, then the star is born, and then they go through this nuclear burning in the core and in shells, and eventually they eject all their matter. And all the matter they eject, either as winds or as explosions, goes to other molecular clouds from which new stars may form. Actually, it's very funny, because if you think of galaxies, when for instance, a supernova occurs, the power is so high that matter is lost even from the galaxy itself, and it enriches the intergalactic medium. But of course, gravity wins again, and this matter which was ejected from the stars, from outside, even from the galaxy, goes back to the galaxy and may form new stars. And eventually, so billions of years after the Big Bang, another not particular special star forms with a planetary system. And one of the planets in this system is right, the Goldilocks forms, so right, just at the right place, just at the right temperature to be able to have liquid water and eventually to develop life. And that star and that planetary system, of course, was formed out of the atoms which started as a Big Bang and then were transformed in other atomic nuclei in the cores of the stars. And this is what we are made of. As Carl Sagan said, we are stuff. We are, aquí lo tenéis. I want you to see this. Whoops, sorry. I want you to see this sentence. We are made of star stuff. So actually, if you ever get too annoyed with someone, if you got annoyed with me because I made my talk too long, be patient, because we are star stuff. And so 60%, 65% of your mass, so you do your maths on your own, is oxygen. Oxygen, which most of it was formed in supernovae. Less than 20% of your mass is carbon, which comes from massive supernovae and not so massive, so low mass dying stars. The nitrogen also comes from there. The hydrogen was in the Big Bang somewhere about 13.7 or 13.8 sorry, 1,000 million years. The calcium in your bones once was in the supernovae, the phosphorus, the potassium, the sulfur, all these matter. So enjoy the stars in yourself and all around, and never lose the ability to wonder at the universe. So here's my daughter enjoying the Big Bang in Cosmocaixa, and I really hope she can there can be the time when I can explain these things to her as well. I actually remember the first time when I heard, actually in a documentary by Carl Sagan saying that we are star stuff. It blew my mind, and it made me know. I think I was 9 or 10 years old, and I knew I wanted to know more about this. I hope you enjoyed that as much as I did, or almost as much. Thank you very much. If you have any question, I'm here.
Hello, Pilar. Really, thank you very much. It has been really, thanks for your time, but it has been really a clarifying and amazing presentation. And hello also everybody. Thanks to be here today. Please feel free to write any question on the chat, and we will share with Pilar as soon as we will have the questions. In the meantime, Pilar, we have some questions for you. The first one is, since you were a girl, did you already know what you would like to become, or it just been, you just explain that you when 9 years old, you start to know, and but if you could explain a little bit more?
Of course. So we had a teacher which showed, I mean, a lot of astronomers and astrophysicists are astronomers and astrophysicists because of this huge cosmos documentary, this old cosmos documentary by Carl Sagan. And I must say that I wanted to know more, but I think I could not even imagine that I could become a scientist. I think, I don't know, when they talk about girls not being able, or thinking that they are not good enough, from more or less from when they are 6 or 8 years old, I think that's what happened. I wanted to be a teacher because I could explain these things to many people, and I'm also a teacher, which is great, but I couldn't dream of being a scientist. And I have thought of that going backwards, and I felt sorry, because why not? Why didn't I dream of that? I did not even dare. And that's a bit sad. I kept reading books on, and I got the Scientific American version in Spanish, and I love reading it, but I don't think I dreamt of being a scientist, probably, even though I loved it, till I finished the degree, and I thought, I'm not going to do any research. I'm not going to keep learning these things. I thought, okay, I have to try to do a PhD. And I started. And it's still going on.
Okay, thank you. Do you think that your career would have been easier if you were a man?
I think probably it would. It probably would, because even this beginning, perhaps if I had been a boy, I would have been able to dream of being a scientist, for instance, even from the very beginning. So I was lucky that for some reason I decided that I would go on, but perhaps I would not. I could have ended up not doing research at all. And also, we're discussing before that there are many small things which affect your even your self, the vision you have of yourself, the perception you have of yourself. I was telling your colleagues just before that in the first workshop, international conference I went, I had to present my work to other scientists, and we were in that workshop, we were about 100 people, only 4 women, and one of the scientists thought I was a waitress, because of course I was a woman. So the first idea that apparently came to his mind that I had to be a waitress, not a scientist. And I remember, so that happened in the welcome cocktail. And when a couple of days later I had to give my talk, I kept saying, okay, I'm not a waitress. I have done my science. I came here to present it. But sometimes you have to rebuild yourself. Other times I found that simply because men are usually bigger and speak louder, it's difficult to impose what you are saying. That's even physical. It's very stupid. It's very stupid. And also you're in a discussion and most of the voices sound like, ooh, like this. And yours is different. And so it's sometimes it's very small things, which sometimes you don't even realize that they affect you, but make things harder. Make things harder. I remember when I just finished my PhD, and they put a poster with a girl in a bikini in the PhD students' laboratory. One girl, of course, got very annoyed, and she was said to be hysterical. And that's not right. So what do you expect from women? Sometimes you get confused. Also, I'm a mom. I have a 6-year-old girl. So this girl in the photo, and you feel guilty if you don't work enough hours. You feel guilty if you don't spend enough time with your mom. And it's getting easier. So men are more and more involved in home, in paternity, but still there's this part of guilt which is very difficult to deal with. So I think it would have been easier. I think many women think that it's all done because we can be an astronomer. So what do you complain of? So, and the point is that most publications are from men, or even as a teacher, students count more on women teachers, but on average, they give better marks when they do surveys. They consider male teachers better. So in many aspects, we are still we have still lots of things to do.
Yeah. In that case, referring what you're just saying, recently is just a comment. I just learned that girls with high capacities, with really high capacities that could be a genius, with a really high IQ, used to hide her skills just to be part of the team. And in that way, they don't show what they are able to do. And it's really, we need to help these girls, not only these girls, but any girls to be confident with herself and understand that everything depends just on they want to do.
It is true. It is true. It is true. The need to fit in. The need to fit in is, and also it's especially in when they are teenagers, which is the moment in which this sort of decisions, so should I do science or should I do other thing, are taken, is when group pressure seems to be more overwhelming. And
seems that the pressure is coming also before the teenager.
Yes.
Is the moment that they need to do the choice, but the pressure is from the beginning.
Yes. Yes. My child. When I ask her, in the breaks at school, girls and boys play in different groups already. And there was this article in Nature, I think in January of 2017, which said that at 6 years, girls start thinking that they are less clever, that they should do things which can require work, but not being clever, and that they are nicer than boys. So it's all the pack of the stereotypes. So if you're clever, you're boyish, you can do difficult things. If you're a girl, you're nice, you can work hard, but you're carrying. So even apparently we treat babies different depending on their sex. So there was this video also the same baby with a pink pajama or with a blue pajama. So if there was a girl, oh, you're so cute, and people were more careful with them. If it was a boy, they would move in, oh, you clever guy, you're strong. So even when we're babies, so.
Yeah. And this is one of the main reasons because Women in Aerospace is trying to become more human, some reference like you. And thank you very much to be here today. I have an additional question. How you value aerospace sector, both positive and negatives, and the impact of aerospace activities on the society?
Well, I think I'm thinking more as a theoretician. So it always think it's a challenge. It's the challenging sectors, because with space you can go to Mars. We made something fly in Mars. We saw it just hours ago, and that's amazing. It's a challenge. It's individually a challenge because it usually involves tough disciplines. So it's individually challenged, and it's a challenge for humankind. So it's the beauty of the challenge, and the beauty, as in the poem, the beauty of anything that flies, and it's the beauty of understanding, because space can be planes and space can be stars. So it's the beauty of understanding and the beauty of getting further, of meeting challenges. The negative part, I think it's the subject today. It's that's still very masculine. It's very so the stereotypes or the way of doing is still dominated by the masculine way of thinking. There are women needed in the sector. So and that's in research, and that's in aviation, in more practical things. And well, it's good that we're here to solve that. But I think it will definitely benefit from women being more involved in that.
Absolutely. And we have some questions. Okay, a lot of people say thank you, muchas gracias, thank you so much for that fascinating lecture and all your insights. Thank you, Pilar. Thank you for the talk, Pilar. It's very inspiring. I'm curious about something. If you don't mind me asking, how can we know that what elements are inside black holes?
But we cannot see beyond the black hole. There's the event horizon, and we cannot see probably, and we cannot know what happened with those elements once, or with the mass one central black hole. So, for instance, if you think of a very massive star, so imagine a star of 30 solar masses. So probably what happened is, after all these burning processes and this sort of onion-like structure and a big hydrogen-rich envelope outside and this ion core, at some moment there's no pressure enough to sustain the star. And if the star is massive enough, instead of leaving a neutron star remnant, then it will all collapse into itself. It will become a black hole. And how much matter enters the black hole? We know what that matter was before entering a black hole, because there was this ion, probably the magnesium and some of the neon layers could also enter. But once it entered the black hole, it probably, it's mathematically it's some point of infinite density, but we don't know more about that. We actually cannot know what's inside there, what becomes of the mass after that. And that's, of course, anything related to black holes is fascinating. And among other things, because it's so unknown. So we know what there was before, we don't know later, afterwards.
Perfect. Marta is asking, how do you think that the fact of being a woman influences when becoming pregnant or having children in a scientific career?
Well, it's well, it depends a lot on people, perhaps on where they were born, but for me it's been very tough personally. So some people can manage better. I have a fantastic, brilliant colleague astrophysicist. When she had kids, her husband stayed at home, so she could perfectly go on with her career. Other women are ready to go to conferences and travel with their babies, and can give a talk with a baby and with holding a baby in one of these bags. So some people take it better, and I I have had to struggle. For me, maybe my age or my background, but I felt this guilt a lot of what I must I do with my time. Also, my my kids slept very poorly for many years. So I think the last 6 years, my brain has been rather fried because she still wakes up a lot by night. So it's been for me, it's been physically demanding and psychologically demanding. At some moment where I found the strength, because it has been very stressing at some moments, where I found the strength was thinking, okay, I have my classes, which I love, I have my stars, which I love, and I have my baby, which I love. I have to choose between one thing I love or another thing I love. So do not complain. But it is difficult, and the point is that this has to be addressed with education and with political decisions, because it shouldn't depend on your specific circumstances. At the UPC, which is the university where I work, there was a decision a high political decision to give a few months with less teaching or with no teaching at all to mothers and fathers of babies. In those months, women decreased the number of publications in those months which were supposed to be dedicated to the baby. So women decreased their scientific production. Men increased their scientific production. So that's not one case that I can tell. So it's more general. So political decisions can be taken and must be clever and must be addressed in a reasonable and special education, because if men are given the time, but they do not dedicate the time to the care of the baby or to share the care of the baby, then we're just still as before. So it's a big issue. Also, some women do not realize that is important. I was also telling before to your colleagues that I was in a colloquium, and one lady had said, well, being a woman never affected me. And a few minutes later, a few minutes earlier had said that she could not lead a project because she was pregnant. So sometimes even women don't realize what's going on, that it's difficult. So it's a big issue.
Based on my experience, I have three babies.
Wow.
And it depends of the context where you work, because some contexts, some companies, some research centers, some teams are helping, and you could do exactly the same thing that you were doing before to be pregnant. And on the other side, there are some teams that are still, it's like you stop your work for a while, and then it's a problem, and you are penalized and you have a problem in the team. I think that mostly also depends of the context where you are working.
Yes.
And the value that they think that your is, but it's feasible. It's feasible. Both things are feasible, and could be also a period of that you are in a standby when you have young children, and then just fly again, and you do absolutely whatever you want, and you can have family. It's not impossible to share both things and both activities, and just the limit are just yourself.
Yes, especially if you love both things, as I was saying, it will give you the strength. If you love work and you love, of course, your family, then you get the strength to do that.
Yeah, absolutely. Okay, Josep says that nice talk. Thanks. What do the gravitational waves will bring in terms of knowledge? And finally, if nobody else has a question, I have an additional question for you. Do you have a message that you would like to share with new generations?
Okay, so first the gravitational waves, or
Yes, please.
Okay, so gravitational, it's been told many times, this sentence, that they will open a new window to the universe, because what we have seen up to now has to do with electromagnetic radiation. So what we have seen is what we can actually see, so the visual spectrum, or we can see X-rays or infrared radiation, or even gamma rays. We can get information from all these electromagnetic radiation. But with gravitational waves, we are seeing information from gravity. We are seeing information from objects which do not necessarily emit gravitational radiation. So, for instance, there's a part of the life of the early universe when we cannot get any light from it, but perhaps improving the technology and the detection of the of the detection of gravitational waves, we could learn much more about the history of the universe, for instance. That would be fascinating. Or we could know much more about events involving huge masses, like these merging neutron stars or black holes. So it's really exciting. It's when I give a talk, and that will link to what I'm going to answer later on. When I talk to younger people, I think, oh, how lucky, all the great things they are going to see. Well, one of the great things, or some of the great things they are going to see, will be definitely related to gravitational waves. In many others, we'll see what happens with Mars. We will see what happens with the search of life for more planets. So one of the first advices is keep your eyes and your ears open to know and enjoy nature and enjoy technological and progresses, because it belongs to all us as humans. And then especially for women, but also for men, one advice would be help and ask for help. So develop and enjoy and exploit, in a good sense, the networking. People like to help, because if we have done an effort to understand something or to get something done, it's great to share it. And people don't have to do the effort twice. So they can enjoy your effort and do further development for other people to use or enjoy or whatever. So help and ask for help. If you're worried, if you have these feelings, we're talking also before the conference about this imposter syndrome. Many people, but 70% of people, so it's a huge percentage of people, think that they shouldn't be in the place they are. They do not deserve being at the uni. They do not deserve their jobs. Everyone else is better. And that's a feeling. That's not reality. So if you share these thoughts with other people, you can understand, because people like Jocelyn Bell, so the discoverer of pulsars, have felt this. Great people have felt this thing. So if you think it's only you who thinks is worse than the rest, you will feel alone. If you share your worries with other people, you will get the support. So communicate, help, and get help. And networking, these sorts of events are fantastic for that. So well done, and thanks for existing and doing your work.
Okay. People say, thank you very much. Congratulations for the capacity to transmit enthusiasm for science. And thank you. The presented points are also fascinating. And for now, that's all. And just my last question, if you have some kind of message that you would like to share with new generations.
Yes, it was that especially. So keep your eyes and your ears open for new developments, for new discoveries in science, in technology, and learn from others, and let other people learn from you. So essentially, help other people, and so this cooperative work actually be active, cooperative. So make that what you learn and your abilities, share them with others. Because at the end, the overall result, the overall progress will be much better. And the satisfaction of the work you do will be much better. I like to think, for instance, as a teacher, that even though what I teach is not going to be used exactly for what my students do, their achievements when my students are involved in projects like this, I participated a bit on their achievements or on the things they are doing. So if you help other people, the reward is much better, and the result, and at the end, the evolution of humans. So not only in terms of knowledge, but also in terms of humanity, if I might say so, is much faster.
Okay, that's all. A lot of thank yous, a lot of congratulations. Thanks. And again, thank you very much to be here today, to find time in your busy agenda. And thanks again to share with us these fascinating lectures, these fascinating topics.
My pleasure.
It's really a pleasure to grow with people like you. Thank you.
Thank you.
Thank you, everybody, to be here.
Thanks. I'll be around. Thank you.
Yeah.
Thank you.
Thank you so much, Pilar, for the talk.
Thank you. I hope I made it not too technical. It was
No,
clear,
no.
right?